In this video, I'm going to give a review of all the midterm review questions that I post online. Okay, so I'm going to talk about solution for each one, and also I'm going to post the lecture notes online so you can view the solutions while watch the video. Okay, we start with the first question is about dot product and cross product of vectors. Okay, just review. This is not new. Okay, so so first question is saying if you're given two vectors a and b vectors, and this we don't specify the dimension of the a and b vectors. It could be any dimension vectors. The a vector has a norm which is 3 and b has a norm which is 2. Okay, so the first question is if a dot b is 0, what is the smallest angle between the two vectors? Okay, so based on definition of the dot product, so a dot b is length of a times the norm of a times norm of b times cosine theta. So theta is the angle between these two vectors. So because here a dot b is 0 and a and b, this is 3 is 2, so my cosine theta here will be 0, right? So which means my smallest angle will be pi over 2. Okay, that's the smallest one angle that can make cosine theta be 0. Okay. The second question says if a dot b is 3, so what is the magnitude of a cross b? Okay, so this is to solve the problem, we have to look at the relation between a dot b and the norm of a cross b. So a dot b is just a norm dot b norm, the length basically, magnitude, time cosine theta. That's what we have for the relationship we have. And a cross b norm of a cross b is a norm dot b norm times sine theta. Okay, magnitude. So that's why the relationship between this one is given by this. One is cosine theta, one is sine theta. Okay, as long as I use here to figure out what my sine theta would be, so I can figure out the magnitude of the a cross b. Okay, so the magnitude of a is 3. If you do the first one, so a dot b is 3. So magnitude of a is magnitude of a is 3, and magnitude of b is 2. So 3 is equal to 3 times 2 times cosine theta. So we can see cosine theta is 1/2. Okay, the relation between sine theta and cosine theta is cosine theta squared plus sine theta squared is 1. So I have sine theta is square root of 1 minus cosine theta squared. Okay, that's why I can use this one to figure out what's the sine theta. Okay, so which means my magnitude of my cross product is given by a magnitude dot b magnitude times sine theta. Okay, sine theta is calculated by this, since I already know cosine theta, right? So which means 3 times 2 times square root of 1 minus cosine theta squared. And cosine theta is already calculated from the first the condition over here gives us cosine theta being 1/2. So this is 3 times 2 times square root of 1 minus 1/2 squared. Okay, so which is 3 times 2 times square root of a 3/4. Okay, so which is 3 times 2 times square root of 3 divided by 2. So the 2 will cancel out, so we have 3 times square root of 3. Okay, so question 1. Okay, let's do the question 2 says, okay, if a f vector has path independent integrals, and C is a curve whose starting and ending point are the same. So what is the line integral of this closed curve? Okay, so here I draw a picture of what that means. So suppose I have a vector field f, and this f has path independent integral, and let's say I draw some C. Okay, it's a curve starting and ending at the same point over here. So because path independent integral, which means I can do this one is the same as any C prime. This is another curve. As long as C and C prime and C, it shares the same starting and ending points. So any line C prime and any line with the same starting and ending points. Okay, so a simple way is like, hey, since the starting and ending point they are the same, for this one is a closed curve, so I can just let the starting and ending point to be the same point. You just start here, ending here, right? Basically starting here, ending here, which means you do a single point. Okay, which means you only integrate a single point. It's like you're doing nothing. You're doing the integration becomes 0. this is a similar idea for the, is the same as you integration of anything like this, right? If you integrate, this is fx, right? You integrate over fx from 1 to 1, for example. You integrate only 1 point, so this will give you 0 because it's nothing, okay? The same concept, okay? So this is question number 2. So question number 3, okay, says let f x y z be the gradient of a scalar field, okay? Fr, where Fr is given by xyz 2x squared plus z. So this one means, if I have this one, this means, okay, what this means? This means is path independence. So path independent line integral. If the gradient is given, this is a vector field given by gradient of a scalar field, okay? And also we have the integral. So compute. So I said, okay, well, C is a path from 1, 1, 1 to 2, 2, 2. I don't specify the path because it is path independent. Because it doesn't matter what the path is like. I want to compute the line integral of C over F over dr. Okay. Of course, one approach you can do is, hey, I want to find a path. Let's say I started from 1, 1, 1. So this is a some point. Okay, let's do it over here. This is 1, 1, 1. So maybe here, maybe I have 1 point, starting point of 1, 1, 1, starting point. And let's say here, 2, 2, 2, they're somewhere over here, right? You can see I'm going to draw a line. Okay, I want to create a line. Okay, a path. This is from 1, 1, 1. This is 2, 2, 2, 2. And you can create a path. Okay, I didn't tell you the path. You can choose any path because it depends on what path, whatever path you select. But another one we talk about in class is if my vector field is given by the gradient of a scalar field, my line integral is just equal to f, the scalar field evaluated by the starting point and to the ending point. You do this, which basically means you do the fr at 2 and 2 and minus fr at 1 and 1 and 1 point. You just do the difference, okay? So by using this, we can use this directly, which means this guy is just equal to this one as mentioned over here, which is mean that I just choose replace this fr by the scalar function that I have over here and evaluate at 1, 1, 1, 2, 2, 2 points differently. So by replacing x by 2, y by 2, z by 2, so this is what I have for this value. Then this is by replace x, y, z by 1, 1, 1, so I get this value. So if you do the calculation, you could have this become 8 plus 8 plus 2, so this is 18 minus 3, so it's 15. Okay. So this is question number 3. Okay, let's go to question number 4. Question number 4 says, let a vector field be given by this vector field, and a path is given by this guy. A path starting from 0 to 1. This is defined a path. I want to calculate the line integral. Okay, this is the typical line integral problem. So what we do is, okay, so this one, so make a notation. You basically do is have r sub t, which is written as a vector form, is t and 2t. So this is defined as by x. This is defined y. So you replace whatever you have here by first by x. So here you basically have t squared and also the 2t squared. Okay, this is your f. So what you do is you replace this one in this form I mentioned for f. So you do this one f written by this form. You replace x by t, y by 2t, so you get this one, and then you take r derivative, okay, and then you take it to dt, and t, the lower bound, upper bound is defined by here. Okay, so from 0 to 1, this is r f. Replace the x by t square t and y by 2t, and then you dot product r dot. Okay, then with respect to t, then you integrate the dot product from 0 to 1. Okay, when I do that, so if I do here's I replace x by t, so I have t squared, and here I replace y by 2t, so I have 2t squared, and this gives me a derivative of this is derivative. Okay, so this is derivative over here. So this is the derivative of t over t is 1. Derivative of 2t over t is 2. Okay, so the dot product will be this guy times this guy plus this guy times this guy. Will be t squared times 1 is t squared plus 2t squared. This is 4t squared times 2 is 8t squared. Okay, so when do them together, you have 9t squared dt over from 0 to 1. So the integration of 9t squared over t is 3t squared cubed. From 0 to 1 is just give us 3. Okay, so this is question number 4. So question number 5 says, how many parameters are needed to parameterize a line? Okay, so basically you have to give a line is, so this example tells you which is line, basically, right? You have basically the minimum one is how many typical parameters you have, xt and yt and zt. Okay, this will define a line. So typically you only have one parameter. You only have one parameter with t. That's y1. So how many parameters are needed to parameterize surface? So typical surface is given by something like let's say r sub I use s maybe x y. You typically have two unit v. Remember, this is something like s1 x unit v. This is x unit v, y unit v, and z and unit v. So just define a surface basically, right? So you also have two parameters because I have unit v. Now here you only have one t, so let's have two parameters here for surface. Okay. Let's go to question number 6. Question number 6 says, consider a region graph, region given by this, which is a quarter of a circle with radius 3. So the first question is, for double integration over this region, I want to find the lower bound, upper bound, and for the limit of the limits. If you want to write it double integration into the form of this one, so basically want to write this one in the form of this one, I don't figure lower bound, upper bound. Okay. So the basic idea for you to figure lower bound, upper bound is notice that here's the order matters. If you do this y and x differently, so this can be a little bit different. So, okay. If this is only the sequence, I want to integrate x first, then integrate y. Okay, so y is outside. You start with outside. The outside says, okay, what is the y for this region? What is the y that I can select, right? Because this is, you start from the top to the bottom, so this is y you can select. You start bottom one is y 0, because below 0 is nothing. You don't have anything here. Above 3, nothing over here. So you have 0 to 3. And here we select for x. So if let's say, if I would say for certain y, what is my range of x will be if I want the integration be in the range, right? In this area. So if you give a y, you can integrate from here. Give y, your x could start from 0 until this very right value. If you go out here, you're gonna be outside this area, right? So the very right one is given by this, because this is y. This is 3, right? So this is 90 degrees. So the length of this guy will be just square root of 3 squared minus y squared. That's why the lower bound is always from 0 for x, and the y upper bound is that. Okay. This is for the first part. The second part says I'm gonna switch that one. What if I switch the order of dy first and dx? Okay. So if I do the dx, okay. So first I want to figure out what is the lower bound and upper bound for x. If you scan it through, yeah, your x can start from 0 until you reach 3. If you move to the right again, so you're not in anywhere. The region does not cover any x that is greater than 3 or is less than 0. So which means this is range from 0 to 3. Now once you do that, I'm going to fix a y. I'm going to fix the x over here to see what is the range of my y, right? In order to stay inside the region, you can start from 0. Your y always start from 0, also start from 0, right? For any x, you start from 0. And the upper bound can reach depending on what x. If x from 0, you can start reach 3. If x is 3, you're gonna go to 0. Relationship dependence, the upper bound is given by this, because this is 9. This is also 3. The radius is 3. This is 90 degrees. So this length, the height, is square root of 3 squared minus x squared. This one you can integrate from 0 to this value. If you're going above, you're outside. If you're going below, you're going outside. That's why it's from 0 to square root of 3 squared minus x squared. Okay. the last part, this next question, evaluate the double integral of this guy. Okay, I want to evaluate the double integral of this guy, which one, this is given by x plus 1. So I have replaced f. I give you actual value of fxy, which is x plus 1, to calculate this double integral. Okay, I can use any one of these. Okay, any of these two approaches. Okay, lower bound, upper bound, but I just select the first one. Okay, to compute that. So according to what I did over here, so this is just given by integrate from 0 to 3 and integrate from 0 to square root of 3 squared minus y squared. This one replaced by x plus 1 over dx dy. Okay, I'm doing some trick over here because I'm doing to split them. One is I want to split them x and plus 1. It's the integration of over x only and integration over 1. The reason I'm doing that is because once we have 1, this is just the area of that. So I don't have to do a lot of computation because that's the meaning of the integration of r1 times dx dy. So that means this is essentially the area of R, my area. Okay, so I don't have the calculation. So which means, hey, this is just the area of, because this area, this lower bound, upper bound is defined by this area, right? That's why it's just this area of R. This area I defined over here. Okay, so the first one I still have to compute that. First one, so I do the computation. So I do the computation here is integration over x. I do the inner integration first. Okay, then I do the external integration right over here. So inner integration is x over x is 1 over x, 1/2 over x squared, evaluated from 0 to square root of 3 squared minus y squared. Okay, this one is just given the area of R. The area is just a quarter of a circle with radius 3, which is just pi times 3 squared divided by 4. Okay, that's a quarter of that. And this one, when you do integration, is 1/2 x squared, right? It replaces this x by this value because it's a square root, right? You take a square, just 1/2 3 squared minus y squared. This one's minus 1/2 times 0, so it's just gone. Okay, so ignore that. And once you do that, you have 1/2 times 9. Integrate that one is, this one is 1/2 times 9y, because this is 9 integration over y is y. This is negative 1/2 y squared is negative 1 over 6 to the y cubed. That's the integration of this part. This first one, this part. Evaluate 0 and 3. Okay, when you do that one, you have replaced by 3 is 1/2 times 9 times 3 is 27. So 27 divided by 2 minus this one is 3 times 3 times 3 divided by 6. So you cancel out 3. This becomes 2. So this is a 9 divided by over 2. Okay. So plus 9 pi over 4. Don't forget about this one. So this one is 27 minus 9 is 18. 18 divided by 2 is 9. And this is 9 pi over 4. Okay. So that's question number 6. Okay, question number 7 is let S be a surface, so the size of S is just this. Okay, just you place 1 over here. Okay, it's just this. Okay, and the T be a cylinder, so its volume is given by this. Okay, so that's it. Pretty straightforward. Question number 8. It says just talk about the relationship, the 3 theorems I mentioned previously. So Green's relationship between sum of the integrals for every theorem. So Green's theorem is concerned with the relationship between the of the double integral and the line integral, which means you can write a double integral into a line integral or line integral into a double integral by using Green's theorem. The Stokes theorem says I can sort of write a surface integral in a line integral or vice versa. The divergence theorem says I can write a triple integral into a surface integral or vice versa. Okay. So question number 9, okay, it says let C be the line, a counterclockwise circle center the origin with a radius 1, which is defined right over here. So the radius 1, and also it's counterclockwise. Okay, its parametric representation is given by cosine t, sine t, t from 0 to pi. Okay, that's how we find the parametric form of this line. Okay, the first question is I want to compute the line integral of C over f1 dx plus f2 dy. You can also consider this as integral over f R. So f is f1, f2. Okay, dr is a line on the line. Okay, so R is defined by my line right over there. Okay, so what we can do is we can just compute this one, right? If we compute this value, it's just by integration from, what I do is just replace, since I already have this one, the parametric form for my R, which is this be x, this will be my y, basically. Okay, if we do that. So what I do is I replace the y by sine t and x by cosine t. So here's f1 is, I also give f1 is negative phi y. So negative phi y, y is sine t, okay? And dx, x is just here, cosine t. So d cosine t plus phi cosine t, 5x, x is cosine t, d sine t, dy is d sine t. Okay, I'll do that one. So negative phi sine t, then d cosine t is negative sine t. Negative sine t plus, there's negative here, so it becomes 5 times sine t squared. Okay, there's a dt over here. And here it becomes 5 cosine t, and d sine t will be just cosine t dt. So 5 cosine t times cosine t, 5 cosine t squared dt. So I pull the dt outside, combine them, put a dt outside. So once I do that, so 5 sine t times 5 cosine t just 5, because sine t squared plus cosine t squared is 1. Okay, so which is 5 integrate 5 over 0 to, over t from 0 to 2 pi. So 5 will be just 5, t is to be 5t from 0 to 2 pi, which is 10 pi minus 0, just 10 pi. Okay. The second question says, recompute the line integral using Green's theorem. Okay, so basically write as a line integral into a double integral. Okay. If I use the Green's theorem, it says the integration of f1 dx plus f2 dy is the integration of this area. This is R is here, is inside this R area, is inside this line, which is a circle. Okay. And over partial f2 over partial x. So f2 is 5x. So partial fx is f2 is 5x. f1 is negative 5y over here. So partial f2 over partial x is 5. Partial f1 over partial y is negative 5. Okay, so this will give me dx dy, also dx dy. So 5 minus 5 is 10, right? 10 over dx dy. Because 10 is constant, so I can move it outside. So the 10 over, you can see this is a 1 dot. Again, so this is 1 integral 1 over area is it's just the area, the size of this area. Okay, so it's a 10 times the area. The area is it's a radius 1, right? Center origin with radius 1 is pi times 1 squared. So it's a 10 times pi times 1 squared. It's just 10 times pi. So that's all for the review. All solution for the review number 3.